Okay, I'm looking at the review problems for fourth test if you got it off Moodle, or the thing that I sent to you, and we'll discuss any of these problems that you might want to. I'm giving you these because the ones I gave you before didn't have any LNs and E's in them. This has some LNs and E's, which are going to be on your test, so we need to be sure that we are comfortable with doing those going into our test on tomorrow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm missing some people that I'm not supposed to be missing, aren't I? Silas has decided to go to physics. Okay. Jerry. Yeah. Okay. Maybe he'll come back. Okay. And Claire went to the restroom. Well, probably sure. What's the rule for the derivative of Ln? Yes. This is about slide 17. I jumped way down there just to be sure we got to the LNs, and we'll come back to some of the others. This is in review 2 that I emailed you, or review problems for fourth test off of the other, off Moodle. But faster and acceleration are two different things. I'm accelerating to move faster, but I'm not accelerating faster all the time. Okay, think of it this way. A rocket is being shot up in the air. Would you agree that it's accelerating? Okay, so it's going to start at 0, so it's going to be getting faster all the time, right? What about what's propelling it up in the air? The booster rockets. They're burning fuel, so they're going to be accelerating slower and slower and slower. They're burning more fuel, so they're going to be pushing with less power. So the acceleration is going to be slowing down, yet the velocity is going to be increasing. Dumb, or you don't follow that?
No, I do.
You do? You're going to follow. If you take two objects that weigh totally different things and drop them in a vacuum, though, they're going to fall at the same rate because acceleration is going to be the same on each one of them. Gravity is going to pull them down. Gravity is going to pull you down at a constant speed all the time. It's going to get clearer as the year progresses, I think. All right, let's look at a few more of these problems. Let's look at the next one, whatever it might be. Ln of x squared. What do we do there? Yes, you can take the derivative of it just like it is, or you can use your power property and make it 2 ln of x, and then take the derivative. So then our derivative would be 2 times 1 over x, which becomes 2 over x. You wind up with the same answer either way, though. Okay? Very good. I think we'll get to the next one. Yep, we'll get there. And all right, let's get this oriented so I can actually write where I want to. Now, notice that this problem is different. I cannot use my power property here. What is being raised to the fourth power? The whole thing. This is my inside function. So, Kelsey, what's my derivative here?
4 ln x.
Very good. 4 ln of x, whole quantity to the third power, times 1 over x, because 1 over x is the derivative of the ln of x. All right? How would you approach this problem? Okay? So, you can do either option here, okay? You can do either one. What Sutton said he was going to do is 1 over the argument times the derivative of the argument. If I do the derivative of the argument, how do I take the derivative of the argument, Sutton?
What you would do is you would derivative the argument well, you have to use the quotient rule.
Mm-hmm.
So you do x squared plus 1 times 1
Okay.
minus 2x times x
Uh-huh.
all over x squared plus 1 squared.
Very good. Now, if I do that, the derivative here that I just wrote down, I can clean that up a little bit. X squared minus 2x squared. That'll get me a 1 minus x squared in the numerator. X squared plus 1 squared in the denominator. What can I do with this fraction over here? This 1 over x squared plus 1? Yes, it could. Now, how does that help things? Made it look less complicated. Is there anything else I can do? I could, but I'm multiplying, so I don't need to do smiling x. What can I do? Or we could just cancel out. There's an x plus 1 here. Cancel it with one of those, and I get 1 minus x squared over x times x squared plus 1. Now, that's using strictly derivative of the argument times the argument. What if I went about doing it this way? What if the first thing I did is I changed f of x to be ln of x minus the ln of x squared plus 1? Well, 1 over x minus 1 over the argument times the derivative of the argument. I get 1 over x minus 2x over x squared plus 1. But that answer is not on my multiple guess. Smiling x now. So x squared times 1 minus x times 2x over x squared plus 1. And x minus 2x squared, I get to 1 minus x squared over x squared plus 1. Which one's easier? I don't know. This, personal opinion, this is easier but longer. Because breaking it up, I don't have to use quotient rule. I have a phobia against quotient rule, so I don't like it, so I steer away from it whenever I can. This gets me the answer. It just takes a little bit longer to get there. I can get there a lot quicker up here the way Sutton said to do it, and I'll get to the same answer. Bottom line is, do it whichever way you want. 1 minus x squared over x parentheses x squared plus 1. That's what I got both times. Yes? Smiling x. Smiling x is when you are adding or subtracting. Smiling x. You are adding or subtracting fractions. Whoops. Fractions. Now, here's what I did. It's first times that minus this times this. The subtraction is just in the middle. This sign is just in the middle of my two things. Denominator times numerator minus denominator times numerator. Yes, sir. Yes, yes. No, we didn't because we canceled that. We had one we could cancel out there. You were trying to find a flaw in the math. It's good. I like that. Okay. ln of t over t squared. Quotient rule. So quotient rule. Can I use?
You will do that eventually.
No. Can't use the property rule. I can't use the property rule because the t squared is not in an ln. Low d high minus high d low all over the low squared. Low d high minus high d low all over low squared. Now, how can I clean up the first part of the numerator? T squared times 1 over t. T minus, what does this become back by here? Negative 2t ln t over t to the 4th. That answer's not there. Yes, I can factor a t out up here. Be careful. I can factor out this t, not the t in the ln. I can factor out the t out here.
Wait, why?
Because this is saying I've got to take the natural log of t before I do anything. It's inside of it. 1 minus 2 ln of t all over t to the 4th. And now I can cancel this t with one of these, and I get 1 minus 2. Keep making my L's wrong. ln of t over t cubed. That would be my final answer. And that one would be on your multiple guess. So you just have to be careful with it, but it's doable. Hopefully I can find some e's in here. Now, what do we want to do here? Why would you split it as opposed to do what Sutton said before?
That's easier.
Seems easier. What's going to happen when I take the derivative of, if I do the way Sutton did before, 1 over the argument times the derivative of the argument? The argument of this is no longer just quotient rule. It's quotient rule, chain rule. A little bit more areas to make mistakes. So I would break it up and make it 1/2 ln 4 plus x squared minus ln of x. I haven't taken a derivative yet. That's still my function. Then I would take my derivative. So now I would take my derivative. It's 1/2 1 over the argument times the derivative of the argument minus 1 over the argument. Any cleaning up I can, could, should do? Now, all of this first term can become x over 4 plus x squared minus 1 over x. Yes, that answer is not on your multiple choice. Now you've got to add these fractions. Here's the mistake you're going to make if you do with your smiling x here, okay? If you multiply x times x, you get x squared. Minus, when you multiply this times this, you get 4 minus x squared. Minus 4 minus x squared. There's the mistake you're going to make.
Wait, why?
Because it's either that or this. It's easier. That would be the first thing you'd write down, because it's subtracting and I'm multiplying a binomial times something. A binomial times 1. So I've got the binomial here. I've got to distribute that negative sign through there in a moment. So there's the mistake I'm going to make. I would probably write it down like this first and then go to the next step. My denominator is going to be 4 plus x squared over x. And now I can simplify the numerator. And lo and behold, it just drops out to be negative 4 over 4 plus x squared x. Find the horizontal tangent lines. What does that mean? Numerator equal to 0, therefore there's none any. Vertical tangent lines. Denominator equals 0. Where's the denominator equal to 0? 0, and that's it. What about vertical asymptotes? Where are vertical asymptotes? 0. Why? 0 is denominator 0 makes vertical asymptote. Horizontal asymptotes.
No.
Horizontal asymptotes. 0. Why is it? How do you get horizontal asymptotes? Degree in the denominator is the biggest, so it's going to 0. Wow, y'all remember lots. Wow, I'm impressed. Good job. Good job. So y'all could just sketch out what that graph looks like. Poof, just like that. Oh, that's it.
We try 57.
57.
Slide 5 on this one.
Okay.
There you go.
Wow. This is the same review. This is back slide 5, he said.
So there's two. So this is the same as tan 5 theta squared.
Yes. You might want to rewrite this like this to make it easier. Yeah. If it were 50, what would the answer be?
0.
Why 0?
That's a number.
Tan of 50 is a number. Very good. Very good.
Oh my gosh.
If that were 50, then we'd be taking the tangent of a number, which is a number, and the derivative of a number is 0. But so what do we do here? Chain rule. So we're going to say f prime, bring down the 2, the argument stays there, to the first power, times, what's the derivative of tan 5 theta? Sec squared 5 theta. But I also have to multiply it by the derivative of 5 theta, don't I? Which is 5. Because I have 2 chain rules in there. See, all right, listen to what we're saying. The derivative of tan 5 theta is sec squared of 5 theta. I didn't say theta there. I didn't say x. I said something x. So what's the derivative of this something in here? It's 5. You have chain rule inside a chain rule. That's what's supposed to mess you up. So we have tan 5 theta sec squared 5 theta. Wow. That's a fun one. Yeah.
We had tan 5 theta in front of the river.
Good question. Let's change the question. We've got this function. Tan 5 theta. All right, so what's your inside function? 5 theta. So that means we take the derivative of the outside, which is secant squared of the same thing, times the derivative of the inside. Derivative of 5 theta is just 5.
But wouldn't it be if it was, wouldn't 5 theta be raised to the first power, so it would be 0 and
No. 5 theta is raised to the first power. 5 is just the number right in front of it. So what's the derivative of theta? The derivative of theta is just like the derivative of x.
Yes, sir, but I'm saying, like, why wouldn't the 5 theta inside the middle not be 0?
Here, why wouldn't the derivative be 1?
Not the derivative, but, like, raised to the power. Because when you
Like that? Come on up. Why is this not to the first power like that?
Yes, sir, and then it would be subtract 1 because you multiply by there, it would be 0. It'd be
Okay. All right. Everybody see what he's saying? He's saying, okay, what if we're saying 5 theta is to the first power? Well, 5 theta is still your inside function.
Okay.
So when I'm taking my derivative of my inside function out here, it's this thing, 5 theta, to the 0 power. What's 5 theta to the 0 power? 1 times the derivative of the inside thing, 5. I've still got, see, if I'm treating that as one thing, I've still got to multiply it by the derivative of that one thing, which is a 5 in there.
Okay. So basically, anytime there's like, if it's raised to the first power,
It acts as if it's not, yes, because it's not going to make any difference if it's to the first power, okay? Yes.
Why did you just find derivative of tan?
Because the tan, this is a totally different problem than this up here. Okay, this is one problem all in blue. This is a different, okay, so the derivative of tan I know is secant squared of the same thing. Remember, the argument stays the same. Okay, then I've got to take the derivative of 5 theta. The derivative of the inside function is 5. Is it 5 theta product rule?
No, like tan and that.
This is not the tangent times 5 theta. It's the tangent of 5 theta. That's right. Yeah. Okay? Let me say this for everybody to hear. There are very few problems that you don't have to use the chain rule on the test. Very few. So if you don't use the chain rule, I'd say, did I miss something here, okay? Yes, sir. Yes, you may. Any other questions on this? If it says find the horizontal tangent line, what do you do? Set it equal to 0. If it says vertical tangent line, you set the bottom equal to 0. Yes, sir.
What's the difference between like finding the vertical and horizontal tangent lines as opposed to asymptotes?
Absolutely nothing. Vertical tangent lines are the same as vertical asymptotes. Horizontal tangent lines are the same as horizontal asymptotes. It's just another way to say it to see if you know what's really going on. All right? Did I say that right? Vertical tangent lines are the same. Vertical tangent line, horizontal tangent lines are just where the max or min is. Yes. Horizontal tangent. Don't worry about finding asymptotes. Okay? Don't worry about finding asymptotes for the test tomorrow. You comfortable with that? Okay. Vertical tangent lines means the denominator is 0. Horizontal tangent lines, the numerator is 0, or the whole derivative is equal to 0. But yes, don't worry about asymptotes tomorrow. I went off on a tangent there. But I'm fun. And y'all caught that. I mean, boy, so many classes never catch that. I mean, wow, that's very good. Wow. Okay. I'll be happy to look at any other questions that you've got here, but I'm going to stop. Yes. 40, yeah. Right. Just this is being raised to. So the derivative of this is cosine of the same thing times what's the derivative of pi x quantity squared? Times pi. Because pi is a number, right? So if you do product rule, you've got pi times the derivative of x, which is pi times 1, plus x times the derivative of pi, which is 0. Okay? Which you could clean that up to 2 pi squared x times cosine pi x quantity squared. There you go. All right. Physics? Okay, go ahead. No asymptote problems. No. Yes. All right. Yes, ma'am. Come on down. Up. Sideways.